All right. Well, hello, Honors Algebra 2. This is our, let's see, would be our second video in our probability part of this unit. This is probably the one section that has the most overlap with the statistics part. So we'll see that a little bit, but it does concern itself primarily with probability, and in particular, finding probabilities using what's called a normal distribution. And a normal distribution is actually a very convenient, very kind of easy way to find probabilities. So let's first off talk about what a normal curve is, kind of what it looks like, and how we're going to use it to find some probabilities. So first off, the normal curve is the graph of a normal distribution that is bell-shaped and symmetric about the mean. The empirical rule is what we're going to use to actually find the probabilities. And sometimes the empirical rule is called the 68, 95, 99.7 rule, but I would say probably more often referred to as the empirical rule. But that does help you to remember the percentages if you remember it as the 68, 95, 99.7 rule. Just as a refresher with notation, I'm using two different symbols. Remember that this Greek letter mu represents the mean, and that this Greek letter sigma represents the standard deviations, which were things we would have talked about previously in the statistics part of this unit. So what this says is that if you go from your mean plus and minus one standard deviation, so that would be this first box right here, that's going to be 68% of your data. So in other words, 68% of the data for the distribution lies within one standard deviation of the mean. So the second one would be that if you go out by two standard deviations, you get to 95% of the data, and if you go out three standard deviations, you get to almost everything. You get 99.7% of your data. So very nice distribution. We're going to find that it's pretty easy to use. So when does it apply? Well, first off, it applies when the population is either normal or the sample is large. And what we mean by large is typically that the number in the sample is at least 30, so the n would be greater than or equal to 30. The other two things were mentioned in the definition is that it has to be bell-shaped, and by bell-shaped you can see right below where I'm writing what I mean by a bell-shaped curve. The other thing is that it has to be symmetric about the mean. So not just symmetric, but the mean has to be at the center. So when you talk about symmetric about the mean, that basically means that the mean is at the center of the distribution. So let's talk about using the empirical rule. We're going to separate this curve up into each of its respective percentages. So we're going to break it down kind of piece by piece here. And they used X bar, I'm not sure why, in this picture rather than mu, but remember they mean the same thing. So first off, we were already just told that the middle 68%, so within one standard deviation, is where that data is. And so if you think about it, if you take 68 and split it up into two, that means that each of these pieces is essentially 34% of the data. And again, that was just taking 68 divided by 2, got us that 34%. Then if you go out from there, you get to 95% of the data. But notice that that 95% includes that middle 68%. So really, if you think about how much you're adding, 95 minus 68, you're only really adding 27% of the data. So you're kind of already used up 68%. That means you're just adding another 27. But then again, notice that that 27 is still going to be split up between two sections, the same way the 68 was. So if you take 27 divided by 2 is 13.5%. That means that each of these pieces for between 1 and 2 standard deviations, I'm not going to put the percentage signs, but would be at 13.5%. Let's continue to do that. So let's now look at where we've got 99.7% of the data, which is at plus and minus 3 standard deviations. Remember, even though you're at 99.7, you've already used 95% of the data after 2 standard deviations. That leaves you with 4.7% left over for those last two pieces. And so then if you think about it, 4.7 divided by 2 is 2.35. So that's going to be the area for each of these. So when we're talking about percentages, we're also talking about areas. And in this case, the 2.35% represents that area between 2 and 3 standard deviations. There is just a little bit more left over that we didn't talk about, which is that anything from 3 standard deviations and out make up the rest of the data. So if you think about what it would naturally add up to, that would be up to 100%. But again, we've already used 99.7%, so there's not a whole lot left over, just a measly 0.3%. which even that has to be divided by 2 for the two sides, which means that 0.15% is what's left over for the remaining two pieces. And that's not between 3 and 4. That's everything from 3 standard deviations and out from there. Okay, so we're now going to use this information to answer some questions about different scenarios. So we're going to see how this is kind of a nice setup that we've got anytime something is normally distributed. Okay, so in this first example, according to the CDC, the heights of 12-year-old males are approximately normally distributed, so that's important. That's what's going to tell us that we get to use a normal distribution, with a mean of 149 centimeters and a standard deviation of 9 centimeters. Sketch this distribution, labeling the mean and the points 1, 2, and 3 standard deviations from the mean. So when you sketch a distribution, first thing you'll do is create your number line, and then you'll sketch a normal curve as best you can. And even mine isn't perfect, so yours won't be either. That's okay. But then what we're going to do, it tells us it wants us to give the mean, which is always going to be the center, and then it's going to go out by 3 standard deviations in either direction. So 1, 2, 3, and 1, 2, 3. Notice that when I make those, that I try to keep the distance in between them roughly the same every time I draw it. Now again, it's not going to be perfect, but that distance along the line at the bottom should be about the same. Okay, so now let's label our mean. They told us the mean was 149 centimeters, so that will be what we put at the center. And it tells us then that we were using a standard deviation of 9 centimeters. So every time you go up by a standard deviation, you go up by 9. So 149 plus 9 is 158. Then go up by another standard deviation, you're at 167. Go up by another standard deviation, you're at 176. Going the other direction, you're just going down by 9 each time. So that would put you at 140. Minus 9 again would be 131. All the way down to 122. Okay, so now about what percentage of 12-year-old boys will be above or over 158 centimeters tall? So the first thing you want to do is express this as a probability. So this is the percentage of 12-year-old boys. We'll just call that X, which are over 158 centimeters, so greater than 158. So now to find that probability, now that we've written it with probability notation, is let's look at where that is on our graph. So that would be everything kind of right in here, these 3 shaded regions, which are going to have the same areas that they did up here. So this region right here is going to be 13.5 based on what we had up on the graph above it. This area is going to be 2.35 where it matches, and then this area is going to be 0.15. So if you add those up, 13.5 plus 2.35 plus 0.15, that should get you to about 16% of the data, it looks like. Okay, let's find another probability. So this time, let's look at what percentage of boys are going to be between 131 and 140 centimeters tall. So first off, let's write that as a probability. So we want it to be between 131 and 140. And so we'll use less than signs to say X is between 131 and 140. And again, that area corresponded to 13.5% of the data. So in this case, we don't even have to add anything up. We can just write that probability down. So you can see how the normal distribution can be very convenient to use. Okay, let's take a look at a couple more examples and then we'll be done with this. So before we move on to those examples, suppose that a distribution of test scores is approximately normal and the middle 95% are between 72 and 84. What are the mean and standard deviation for this distribution? So here's what I would think about. 95%, that was taking your mean plus and minus 2 standard deviations is what we said before. So let's look at 72 and 84. And remember, the mean should be in the middle of those two. So if we want our mean, probably the easiest way to do that is to take 72 plus 84 and divide by 2. So what that ends up being is 156 divided by 2, which is 78. And if you think about it, 78 would be halfway in between those two numbers. So then, what's the distance between those? Well, let's just look from 72 up to 78. That's a total of 6 units, whatever we're using for our units here. But remember that that is 2 standard deviations. So if we want our standard deviation, we've got to take that and divide by 2. Tells us that our standard deviation should have been 3. Another thing you could do if you wanted to in this case, you could always draw a picture. So if you wanted to draw in a normal distribution and then figure out, okay, here's 72, here's 84. We know that those are 2 standard deviations from our mean in the middle. Then you can figure out kind of what is the halfway point, and then what would it make sense for the other 2 values to be. That would just be another way you could do it, working a little bit more visually rather than kind of numerically. Okay, so for the next question, let's maybe label the rest of this. So figure out their distance at 3, so 75 and 81. Can you calculate the percentage of scores that are above 80? So 80 would be just a little bit before 81, and you'd want everything to the right of that. The problem is we can find the area from 81 and up, so we could figure it out from here on, but it's this little piece from 80 to 81 that we don't know what the area is. So I'm just going to put area question mark. We don't know what that is. And it's not as if you can just take the 78 to 81 and divide by 3, because if you can see, they're not equal sections. Some are higher than others. So the answer is not with the empirical rule. And the reason for that, so our explanation here, is that 80 is not a standard deviation away from the mean. So in order to use the empirical rule, you have to be on a standard deviation away from the mean, whether it's 1 or 2 or 3, but you can't be 1.4 above the mean, or whatever it might be. Now, you can actually still calculate the probability. In fact, that's something we do in AP statistics all the time. We actually use a calculator command, which actually can find the probabilities for you without having to use the empirical rule. And so if you'd like to see that, you'll just have to take one of my stats classes. We just don't have enough time for it here. Okay, so in this next example, survey of the teachers at Shawnee North found that the mean morning commute time to work was 18 minutes and standard deviation was 4 minutes, and that the data was fairly symmetric. Sketch a normal curve showing the commute time at 1, 2, and 3 standard deviations from the mean. So we'll start that the same way. We'll start with our normal distribution. It did say that it was fairly symmetric, and if you think about the number of teachers at North, there is certainly more than 30 teachers, so we can go ahead and make the assumption that it's a normal distribution. The mean, it says, was 18, and then going out by 3 standard deviations either direction. I'll just get those drawn in here. We're going up and down by 4, so this would be 22, 26, and 30, and then 14, 10, 6, and below. So what percentage of teachers at North drive more than 14 minutes or more in their commute? So that would be this area right in here. So to write that with a probability notation, we're going to say that probably the x is more than 14. And I guess 14 minutes or more, greater than or equal to. Here's the deal, greater than or equal to and greater than actually ends up being the same exact probability, so you don't do anything differently in calculating that. And if you want to know why, feel free to email me and I can give you a little bit more explanation on that. So let's find the probability. And I guess one thing you could do is you could add up, this is 34, this is 34, this is 13 and a half, this is 2.35, this is 0.15. I suppose you could add all of those together. The probably easier way to think about this is that the normal curve, half of the normal curve is 50%, which means it would probably be a lot easier to do this. If 18 is in the middle, that's 50%, plus you just have another 34% on the left side, and 50 plus 34 is 84%. I think that's a little bit easier computation to do. Okay, for the next one, about what percentage of teachers drive more than 26 minutes in their commute. So now we're looking at this piece of our graph there. So again, writing this as notation, driving more than 26, x greater than 26 is equal to, we just need the area for that pink shaded region, which would be 2.35 plus 0.15, tells you that only about 2.5% of teachers at North have to drive more than 26 minutes. Okay, one more example, and then I think we'll be done with this section. So, in this example, 2,000 freshmen at State University took a biology test. Their scores were distributed normally, with a mean of 70 and a standard deviation of 5. Label the mean and standard deviations from the mean. All right, which this time is kind of nice. It already gave us our graph here. So we had 70. I'm just going to draw on the rest of these lines as well. Then we're going up and down by 5 each time. So 75, 80, and 85. And then going down would be 65, 60, and 55. Okay, so for part A, what percent of scores are between 65 and 75? So first off, writing that as a probability that you're between 65 and 75, and you're looking at this piece right here. So that would be between 1 and 2 standard deviations. That one's pretty easy. In fact, you can just directly use the empirical rule for that one. That was 68%. For the next one, we want the percentage of scores that are between 60 and 70. So 60 less than X less than 70. And for that one, you're looking at these two pieces right here. And then as a reminder, you've got 34% here, 13.5% here. If you add those two together, you get 47.5%. All right, going a little bit quicker here since we've done this quite a few times. What percent of scores are greater than 80? So probably the X is greater than 80. So now you're looking at just a couple of pieces. You're looking at this piece here and then kind of everything out from there. So that's going to be your 2.35 and 0.15, which we've already done a couple of times, adds up to be 2.5%. All right, for the last two, these are ones we don't even have to use the graph for necessarily. What interval captures 95% of all students? Remember, that's plus and minus 2 standard deviations. So that would be going out by 2 in either direction. Tells you that 60 to 80 is going to be the interval that captures 95%. And then remember, 99.7% is just plus and minus 3 standard deviations. So that would be going out by 1 more, 55 up to 85. There would be 99.7%. All right, we've got 3 more sections left, but that is our last section for this week. So this will be the last section covered on your quiz this Friday. Have a good day, guys, and I will talk to you next time.